Okay, we mentioned this previously, the enthalpy of hydration, which is going to be important because, like we said, if we want to dissolve an ionic substance, we're going to have to break up the crystal lattice. So we're going to have to overcome the lattice enthalpy in some way. And the only way we can get that particular energy back from the energy bank is through hydration. Okay, so a bit of a definition for you. Enthalpy of hydration, it's the heat change per mole for the hydration of the gaseous ion with enough water so that there's no further heat change on dilution. Okay? So you add enough water to completely hydrate 1 mole of gaseous ions. Now the example here is a positive ion, but it could be a negative ion. And if we've got an ionic substance, we're going to have to add together the hydration enthalpies of the positive and negative ions present, aren't we? Okay. So this is what it looks like. You know that water molecules have got permanent dipoles. So you've got a negative end and a positive end. So the sodium chloride, when it dissolves in water, the sodium ions start floating around and the water molecules line up around them with the negative end closest to them, and that stabilizes the sodium ion. And this is an exothermic process, so energy is released, so it's a more stable situation, arrangement of the particles. And the same goes for this. Chloride ions, negative charge, so the positive ends of the water molecules get close and they stabilize the chloride ions, and it has its associated hydration enthalpy. Okay? And that's how we can break down the crystal lattice. Now, breaking down the crystal lattice, remember, lattice enthalpies are exothermic, and that's when the crystal lattice forms. So breaking it down is obviously going to be endothermic, isn't it? How big the hydration enthalpy is depends on how close the water molecules can get to the ion. So with very small ions, the water molecules can get close, so the hydration enthalpy will be greater. You're producing a more stable arrangement of the particles present. Okay, so small, highly charged ions have the largest hydration enthalpy. That stands to reason, doesn't it? Right, now, if the energy released when these ions are hydrated is roughly the same as the lattice enthalpy, then there's more chance that a substance is going to dissolve. Dissolution of the solid is favored. Okay, so the energy required to break down the lattice is recouped when the ions are dissolved and hydrated. Yeah. So delta H of solution would be the overall enthalpy change when we dissolve 1 mole of a substance. If we dissolve 1 mole of sodium chloride in water, then we get what's called the enthalpy of solution. And it's going to be an addition, some kind of sum of the hydration enthalpies and the lattice enthalpies. And that's the equation you need to use. I'm going to show you where we got that from in a second. But the enthalpy of solution will be the hydration enthalpies, which will be exothermic, minus the lattice enthalpy, which will be endothermic. So you think about this mathematically, if this number has got a bigger magnitude than this number, then delta H of solution overall is going to be negative, because this starts off as being a big negative number, and we subtract a negative number, so that becomes a plus, doesn't it? And if this number is a smaller magnitude, then this overall will be exothermic. Okay, so low solubility can be the result of large delta H lat, if this is very big, very strong lattice, or a small sum of hydration enthalpies. It's always going to be a combination of a play on the comparison between these two numbers, isn't it? Delta H solution is positive if that's the case, and dissolution would be less favoured. Still possible. We'll talk about that later on. Now, draw a Hess diagram to represent the energy changes when the salt, MX solid, is completely dissolved in water. Write the general equation for delta H solution, which is what we've got here. So we're trying to reproduce this as a Hess diagram. There's my solid MX, and I want to dissolve it in water, don't I? So here we've got to think about what it would look like to get from here to 1 mole of crystal lattice. So down here, think about what you need to fill in. I'll let you have a go at that. You can stop me for a second. Okay, the logical place to start is 1 mole of gaseous ions of each of the M and the X, and that gives me my lattice enthalpy. If I take these gaseous ions and I put them in plenty of water, then I get aqueous ions. So my delta H of solution is going to be against the arrow, so minus delta H lat plus the sum of the hydration enthalpies. And that's how we reproduce this equation. Okay. Right. Read the pages and answer the questions.